Hello, this lecture will cover pages 9 through 14 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Basic Concepts, Chapter 1B, Power and Passive Sign Convention. We're going to start out on page number 9, and we're going to talk about power. Power can be steady state, DC power, capital P, or it can be time-sensitive parameter, small p of t. And it's measured in watts. The power formula, power is always equal to the voltage times the current, and it's measured in watts, or the time-sensitive formula, which we'll use a little bit later, P of t is equal to V of t times I of t, and that's also in watts. So we have some previous expressions for voltage and for current, so we can come up with a representation equation for power. Power is equal to V times I. Well, we know V is the derivative of work with respect to charge, and we know the current is the derivative of charge with respect to time. Notice the charge cancels out, and power is simply the rate of change of work. Think about the physics of what we just explained here. Power is dW dt. It's the rate change of energy with respect to time. Some energy or work, same thing. The rate change of energy or work with respect to time. Therefore, the change in energy, delta W, is equal to the integral between limits of P dt, which is equal to the integral from T1 to T2, those limits, whatever they may be in your problem, V times I. And you're going to have problems. You're going to have some homework problems. You're going to have to use this. But here's all the information you need. Example homework problem. Here's an example. The charge entering the positive terminal of a resistor is Q of t is equal to minus 10 e to the minus 2t, and that's in millicoulombs. If the voltage across the element, V of t, is equal to 80 e to the minus 2t in volts, determine the energy or work delivered to the resistor that will be dissipated in the form of heat, by the way, in the time interval 0 is less than t is less than 20 milliseconds. What I would recommend in all of these problems is to draw a picture of what you have. I mean, I'd literally just go ahead. It looks sort of simple, but I'd just go ahead and draw yourself a block diagram, show there's the element of the resistor. That's the positive terminal. Here's the negative terminal. You come out and label what you have. Okay, well, here you have Q of t. You know Q of t is equal to, and just write it in if you have to, and the voltage across this element, a T, is equal to, and write this in even though you have it here. And then what do you need to find? Determine the work or energy. Now, if you have everything down, boiled down to this, this will help you in these problems, I'm telling you. You know the charge with respect to time. You know the voltage with respect to time. And you're trying to find the work. You look for equations that will help you solve to that end. Here's your solution. Since we know Q of t, we already know Q of t, we can find I of t, and it follows that the change in work is what we're looking for is equal to the time limits. We're going to have 0 here and 20 milliseconds up here. That's your limits up here of P dt, which is equal to the integral between the limits of VI, V times I dt. You already know V, you just have to find I, and we can find I from Q of t, because we know I is equal to the derivative of Q with respect to time. And these derivatives and integrals in this course are not going to be difficult. They're going to be pretty easy. I mean, the derivative of this 10e, of this minus 10e to the minus 2t is you bring the exponent out, multiply it times the coefficient, and rewrite the exponent for the of e. I mean, who can't take this and take the derivative of that? It's pretty easy. 20e to the minus 2t, and that's in milliamps. Now we know our current, now we know our voltage, we put it into the integral equation, we solve a simple integral here, bring in the constant out. Keep in mind this is millivolts here. There's millivolts carried along here, which is going to give us the millijoules for the answer. But you solve the integration, you end up with the work, or the energy delivered to the resistor that's going to be dissipated in the form of heat is equal to 30.72 millijoules. Nice problem. Passive sign convention. This is very, very important. Every semester I talk to the students about this, and some students take me seriously and some students don't. You have to understand passive sign convention. You have to use it or you won't be able to write your equations and you'll get confused by the time we get to chapter 3. What is passive sign convention? With passive elements like a resistor, conventional current always establishes a positive plus voltage reference on the terminal that the current enters with respect to the terminal that the current leaves. It is very important that from this point forward in the course that when you show direction of current through a passive element, I don't care if it's a resistor or after midterm a capacitor and an inductor, because all three of those are passive elements, but up until midterm we only deal with the resistor. Capacitors and inductors are later. But it's very important that from this point forward in the course that when you show current direction through a passive element, you label the voltage polarity of that element as shown below. I showed you 3 examples here. If you have a resistor and you're showing current going in this direction, and it's always conventional current. So let's say you assume it's that direction. You put a plus there and you put a minus there. What if you show current going in this direction for some reason? You put a plus there and a minus there. What if you show a current coming down? You put a plus there and a minus there, and a current going up. You put a plus there and a minus there. Try to get this as soon as you can. I'm going to have you do it constantly in this course, but you have to show passive sign convention so your equations will work for you. The voltage difference across any passive element is always given by the voltage difference, in this case across R1, the resistor R1, is always equal to the voltage on the positive most side minus the voltage on the negative most side. This explains it all here. So the voltage, if current flows in this direction, from left to right, you put a plus here and you put a minus there. That's the passive sign convention I just discussed. And then the voltage across that resistor, you always start with the positive most side, VA, minus the negative side, VB, and there's your expression. That's the voltage difference. Keep in mind that voltage is always across something. You never measure voltage through. Voltage is across. And current is always through. Current always flows through something. It's whole charges or electrons in motion. Voltage is a difference. It's measured across. Voltage measured across, current through. Resistive, this is on page 12. Resistors are passive elements because they absorb energy and give off heat. The power equation tells that power is equal to the voltage times the current, and that's in watts. So as a general rule here, when the current enters the positive terminal of an element, that element absorbs energy. When the current enters the negative terminal of an element, that element supplies energy to the circuit. Think about general rule here. And let's go back and look here. Let's see if I can't find a circuit here that we could... Well, we'll just draw a quick circuit here and I'll show you how that works. Here. Let's say we have a simple series circuit. I'm just showing you 2 resistors here. And you're going to know the direction of current. There's plus, minus. Let's say make that 10 volts. Let's just call this R1 and let's call this R2. You know current flows in that circuit from here to here and back, clockwise. So right away, put a plus there, put a minus there, put a plus there, and put a minus there. Because this current, and I'm not going to specify conventional current or electron flow. When I say this current in this course, I'm talking about conventional current flow from now on. So this current in this circuit enters the positive terminal of this element, and it enters the positive terminal of this element. So the power that we would calculate here, and we haven't done it yet, but the power we calculate is absorbed. The power here is absorbed, and look what the current does here. It enters the negative terminal, and if the current enters the negative terminal, it supplies. So the energy is, this source of EMF supplies energy in the form of watts to these two resistors which absorb them. And consequently, you're going to see the conservation of energy in our problems. When you calculate the energy supplied in a circuit, it'll always equal the energy absorbed. Let's put another current source down here. And let's do it this way. Let's make it 2 volts. I just put a voltage source down here. I just drew another voltage source down here. This is going to supply energy. This is going to absorb energy. This is going to absorb energy. And what's this one going to do? If it goes in the circuit like this, it's absorbing energy. Look at the polarity. The current is entering the positive terminal just like it is here and here. This would be absorbing energy. If you turn it around, it would be supplying energy. Turn this around, make this the plus side and make this the negative side. Make that plus and make this minus over here. There's a plus and there's the minus. You could replace this with simply 12 volts and get rid of this, because they'll be aiding one another. You have 10 volts here and 2 volts here. If it has the same polarity, minus to plus, you could just replace this with 12 volts. In both cases, this would be supplying and this would be supplying if the polarity is minus to plus, because the current is entering the negative terminals of both of those. I want you to see example 1.1 in the textbook. It's a good example. I want you to look it over. It looks like this. There's example 1.1 in the textbook. Okay. Make sure you look it over and you understand it. Additional examples they have in the textbook I show you here on page number 12. Here we have an element. We don't know what it is. It's just a block. We don't know what's inside that. We have 12 volts across. We measure 12 volts across it, and this is the polarity. And the current, and this is the direction we measure, and it's 4 amps. So the power is always equal to voltage times the current. That's the power formula. That's 48 watts. Now what the author does is he calls this a negative current if it's flowing into the negative terminal. And if you get a negative value for power, he says that's being supplied. This is supplying power to the circuit, this circuit over here. But this is just a convention that this author uses. We're not even going to worry about that convention. There's no such thing as negative power and positive power. There's either power that's absorbed or there's power that's supplied. So what we're going to do is we're going to say power is equal to 12 times 4 is 48. And we're going to look at the direction of the current. And if it goes into the negative terminal, we know power is being supplied by the element. And we're not going to show negative. Look down here. In this case right here, power is being absorbed by the element. How much? 8 watts. Look down here. Power is being supplied by the element. 8 watts. You don't have to calculate negative. Just use the absolute value. Just take the absolute value of the voltage and the absolute value of the current, multiply them together to get the power, and then use the convention I told you about. And in this case right here, current flows into the negative terminal. It's that device is supplying. It can't be a resistor. It's going to have to be a source because of this. Page number 13, example, homework example. Here's a simple series circuit with 2 devices, device 1 and device 2. I want you to calculate. There's the voltage across device 1, there's the polarity, there's the voltage across device 2, there's the polarity, and here's 2 amps. It's a series circuit. There's 2 amps here. I didn't have to show this 2 amps. There's 2 amps here, and there's no place for them to go other than here. So there's 2 amps in that loop. Power in that device is 12 watts absorbed. Power in this device, 36 watts absorbed. Power in this device, the 24 volt source, 48 watts supplied. And check your conservation of power. The power supplied has to be the power absorbed. And if you add these up and it's equal to that, check, it works. Do a quick check on your work. Note, when measuring voltage with a voltmeter or current with an ammeter, the positive plus red lead of the meter always must match the positive sign convention of the current flow in the circuit. This is because both voltmeters and ammeters are also passive elements. We're going to see this in the first or second lab. Also, since you measure voltage across an element, voltmeters are placed in parallel with the element. And since you measure current through an element, ammeters are placed in series with the element. If you look down here, we have a voltage source of E, and we have a single resistor. So this is all we have. We have a battery, and we have a go-through resistor. We want to measure the voltage across that resistor. So here's your voltmeter. The red plus lead goes here, matches the plus on the resistor. And the negative, black lead, if you will, goes down here. It matches the negative lead on the resistor. That's how the voltmeter would go into the circuit. Remember, voltmeters measure voltage across the difference. The ammeter has to be in series. It has to have the same sign convention of a resistor. So the ammeter, you'd have to break the wire. Voltmeters, you don't have to break the wire, but with an ammeter, you have to break the wire and you have to put the ammeter in series. So all these whole charges flow through the ammeter in the same convention they would a resistor. Since that's a passive element, you'd put the red plus lead here on this side of the resistor, and the negative black lead of the ammeter would go in return to the voltage source. You'll be doing this in the lab. In page 14, very, very important equation in electrical engineering, Ohm's Law. Ohm's Law simply says that the voltage is proportional to the current. This is what really Ohm's Law is. This isn't Ohm's Law. Ohm's Law just says the voltage is proportional to the current. As the current goes up, the voltage goes up. As the current goes down, the voltage goes down in a linear element. And we're just talking about resistors now. So here's an equation. What makes this proportionate symbol an equal sign? It's the resistance value. V is equal to I times R in volts. A lot of people refer to that as Ohm's Law. It's nothing more than a linear equation. Remember your Y equal mx plus B? Well, if you just look at this, it's really V of t. We'll do the time sensitive here. V of t is equal to R times I of t plus 0, where the slope is nothing more than the resistance value. Think about that. M is nothing more than the resistance value. And the intercept of the y-axis is 0. So when you plot resistance values, this is going to be V up here, V of t, and this is going to be I of t here. There's your x and y. And resistance values look like this. One resistance value will plot like that. Another resistance value will plot like that. Another resistance value would plot like that. Let's call this R1. Let's call this R2. And let's call this resistance value R3. They're all linear. Resistance values are linear. Obviously, in this case right here, since R is the slope, R1 is a greater value resistor than R2, and R2 has to be a greater value resistor than R3, arbitrarily speaking. Other forms of this equation are isolate current. You get current is equal to voltage over resistance, and that's in amps. Or if you know the voltage in the current, you can say resistance is equal to voltage divided by current, and that's in ohms. Where on all these three equations, V is the voltage in volts, I is the current in amperes, and R is the resistance in ohms. Then we already know the power law. The power law is equal to voltage times current. DC. The time variant. Power with respect to time is equal to voltage with respect to time times current with respect to time. It's the same power formula. Also, if we take some of these variables, V and I here, and we substitute in some of the Ohm laws, some of these derivatives of Ohm's law up here, you can see that power can be represented as I squared R in the DC sense or in the time variance sense, and it's in watts. I'm just substituting up here voltage is I times R. Voltage is I times R. And I get I squared R for power. Down here, I'm substituting for resistance. I'm substituting in for current. I'm substituting for current here, which is V over R down here. And V over R ends up with V squared R. Power is equal to V squared divided by R in watts. So here's an equation for voltage if you have I or R. Here's an equation for current if you have V and R. And here's an equation for resistance if you have V and I. And here's an equation for power if you have V and I. And here's an equation for power if you have I and R. And here's an equation for power if you have just V and R. Whichever one works for you. And that concludes this lecture.